In this example, I'm going to demonstrate the construction of a second degree Newton's polynomial and for a data set. So I define the data set xt and y. These are the data points. So I take some values 2, 4, and 7. And just for example, I generate the y values from the natural log of the x values. So I got the 3 values. Okay. And according to Newton's formulation, this yd values, these are f of x naught values. And here, let me generate the zero order divided difference. Here I will generate the first order divided difference and the second order divided difference. The first order divided difference, these are just the values of ordinate. Then the first order divided difference, it is not going to exist for the first time, for the first point. So for the second point, it is the slope value. So I can compute. This should be the value of y2 minus y1 divided by x2 minus x1, which is at b6. So that's fine. And then to compute the second constant, I require this value as well. So first order divided difference have been computed. This value will be equal to b naught. This value, the diagonal entry, is b1, and here b2 value is going to appear. So this will be computed from the first order divided differences. So this value minus b8 minus g7 and divided by the x2 minus x naught. So it should be noted that at the second order divided difference, we have the spacing between points as 2. So 2-point difference is there. We have got this value for b2. So these are the values. And now for any interpolation value, let's define some points x and their corresponding approximate values. So for example, if I require an interpolation value for example for 3, so it should be computed as value b naught. So I can write $6. So this is b naught. Then b1, it is b$7, okay, times x minus x naught. So I have to provide x value. Okay, this is x minus x naught. X naught is at b$6 plus b2 value, which is at h$8. So you can notice it has been rightfully picked from the respective cell. Then the x value, x minus x naught. So again, I can pick from b$6, x minus x naught times x from m6 minus x1. So x1 is at b$7. So that's the value generated by the polynomial. So 1.072. So it seems to be between the values 0.693 and 1.386. So it seems the calculation is right. So if you require a value at 5, so now it will work like pointers. The moment you change the value at this cell, that will be the respective value of y will be obtained. Now let's generate the complete polynomial of second degree. So I define it, even though that is not the interpolation in the rightful way. However, let's, for the time being, let's use it. So plus 0.2. So we have get to 6.3. Okay, let's move ahead. Well, the interpolation is valid for all the x values which are between 2 to 7, right? However, since we have the polynomial constructed, we can follow it beyond that. So all the values will be generated. And then let's do the plotting. To see the data points and to see the curve. So first data points. Okay. Select data, add a series, x values, and then y values. So we have got 3 points. Then add a new series. And for this x values, let's plot up to 8.5. Vectors size must be balanced. And behold. So from the blue points, these are the interpolated values. That's the polynomial. A second degree polynomial resembles a structure of the parabola trajectory. So you should add the x labels and y labels while developing professional or report plots for the reports and thesis.